Alright, hello everyone. Let's do today's challenge. Count complete tree nodes. What's that? Given the root of a complete binary tree to the number of nodes in the tree, every level except possibly the last is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. Again, between 1 and 2 to the h nodes inclusive at the last. Because that's 2 to the 0 and 2 to the 1. This one could be 2 to the 2. Well, actually, no. 2 to the 2. Yes, 2 to the 2. The tree is complete. So what will be the fast way to get this, right? I mean, what we can do, how many we're talking about? I mean, we can just BFS it, right? But how do you know the depths? Well, I can go to the left. Left will tell you the depth. Okay. But it won't tell you how many is on the last. That's the thing, right? You want to know how many is on the last row. But we know it's a complete binary tree, which means Can we guess where it is? I guess we can, right? How? How'd you guess? Well, you go all the way down left, you know the levels, right? You know the levels. So if I know the levels, what I can do is, and that might as well just do the entire thing. I mean, we can solve this easily, but I feel like there gotta be a better way to do this. I can solve this first and then figure out a better way to do it. I don't know, man. How'd you tell the length of the last one? I'm thinking binary search. Like, if we go all the way right. But then, how do we zigzag to the middle? I'm just gonna solve it in a stupid method. And then, yeah, kind of just get it done with. But yeah, I didn't use the condition that it's a complete binary tree. Yeah, but this has nothing to do with anything. It's just an algorithm to count nodes. I mean, which I think will work, right? But oh, okay. Yeah, which will work, but it's not. Right? It's not the one that we want. Didn't take advantage of the tree being complete. And how do I take advantage? On a complete tree, we filled everything. So if we know the height, we'll know it. But then the question is the last. How do I know about the last? Yeah, I go all the way right, all the way left, and all the way right that we know. But in the middle, how do we handle in the middle? Hold on. It's a complete tree, right? So everything is fully connected. But the last one is not so sure. So what we can do, if we go to the left side, then we can go down to the bottom. Then we know the height, right? Then immediately we know how much this is. Now we need to figure out how many this, the last one, is. How do I do that? I mean, all we need to know is the... Actually, I don't know. I know this. I know the last. Before the last, I know how many there are. Because each individual is also a full tree, right? So the height of the tree. The height of the tree. If I have two subtrees, if the left subtree has a certain height and the right subtree has a certain height, I seem to know. If the two subtrees, right, if my left and my right has the same height, that means, I mean, the height is defined as the longest, right? That just means the left is a complete tree, right? It's like the last row filled everything, so we have to go to the right. And then again, oh, it's a binary search. Then we will find, right? We'll find a certain situation where the left is a full, right? And the right is, like, the two heights are different. If the two heights are different, then we go on the left subtree, right? And then we keep trying, and two heights are different. Same, and eventually we will pinpoint to that one node who has a left tree is 1, right, and the right tree is 0. That's the moment. When the right subtree becomes 0, that's the moment. So when right is 0, that is the node, right? So we find the node where it split the two. But then the question is, okay, so I know that, but how does that help me? Right? We know, well, what it can help is when I split the two, right? So I'll have the root, that's 1. And I go 2, and if the left and right are both the same, then the left is a full, okay? Because at left I get a height, the right I get a height, so I'll get a height for both. And when I get height, I just go down the left path, right? So I get a height on the left, I get a height on the right. If they're the same, then the left we already know, so we just try to find the right. That is more promising. So we need a get height. We have a node, right? And then we'll return an integer. Say if not node, return 0, right? So that's the height. Because we say this is 1, 2, 3. Then that's 2 to the third minus 1. That's the total number. All right. So if it's empty, that's a 0. Height is 0. Otherwise, we can say get height. We only need to go node.left. Right? We only need to go node.left, and then its height plus me. So we just return 1 plus, which I think is pretty stupid because I can just go if not node return 1, else we say res equals, actually we can put here and then circle res. If node, while node, then while node, res plus equal 1, and then node equals node.left, and then we'll return res. Right, so that's get height. So then count. Oh, we can actually, can we do it directly? Hold up. So now I want to count nodes, right? So how do I count nodes? I go my left and go my right, right? The subtree. So I go my left subtree. So we say HL equals self dot get height root, or say if not root, return 0. All right, otherwise the rest equal 1 because that's the root. And then we have the left, and then HR equals self dot get height root dot right. Okay, so I have the left and right. Then we say if left is equal to right, when left is complete, left subtree has leaf also complete. So in that case, we'll say return, because left, right, left is going to be and when we count, we say this is level 1, 2, 3, right? So I have 3 levels, so it's going to be 2 to the this minus 1, this is on the left, right? And then we actually say 1 plus 1 is the current root, so I have left, and we place self.count root dot right. No, I don't need this. Else, right? Else then will be left will be larger than right. Then we will return 1 plus 2 h right minus 1, right? Because the right is smaller. And then we'll plus self dot count nodes root dot left. Right? Eventually we will hit a point where root dot left is 1. So HL is 1, HR is 0, right? So they're not the same. Then this one by itself, and then both are 0. That's a none, that'll be 0. Okay, let's try this. Yep, I think this is probably the smarter method. Yes, this is taking advantage. So this method takes full advantage of the tree being complete. We use binary search to eliminate a complete tree at each step. If the max height of the 2 subtrees are the same, that means the left subtree must be complete. Otherwise, the right subtree must be complete. With this, what should be logN. Each step is logN, and yeah, I think that's logN. Say it's logN. What's the previous solution? Oh wow, that's exactly what I had this time. Logn squared. Yeah, I was thinking about logn squared. So I was able to code it like Mr. Parkman. Actually, I think it's better, right? It's cleaner. All right, so we're done with this. Good. Let's solve. Let's take a look what this one is. Stock price fluctuation. You're given a stream of records about a particular stock. Each record contains a timestamp and a corresponding price. Due to the volatile nature of the stock market, the records do not come in order. Ooh, even worse, some records may be incorrect. Another record with the same timestamp may appear later in the stream, correcting the price of the previous wrong record. Design algorithms that update the price of the stock at a particular timestamp, correcting the price from any previous records, finds the latest price of the stock based on the current records. The latest price is the price at the latest timestamp recorded. Okay. Finds the max price the stock has been based on the current records. Finds the mean price that has been. Okay. So we just need to find a max price and the mean price. Well, this should be easy, because every time we get a new, we just update the max, update the mean, right? And then do not come in order. Some records might be incorrect. The same one, so when we have the same timestamp, correcting the previous wrong. Now we'll update a particular. So when we update, oh, that's the thing. When we update, ooh-wee. When we update the previous, then I want everything to change. Damn. Okay, so we can create another object that has timestamp, that has price, and then we create a heap. So one of the heap will be based on timestamp, but how do you change it? God, Lord, how do you change it? Exactly, how do you change it? Well, if timestamp is a key and the value is our price, but then how do you know what is your latest timestamp? Well, we can put all the timestamp into a heap. So we'll always know when the latest timestamp is, and then we look into the hash map, then we get the price. That can be solved. How about a max price? Well, max price. There are ways to do it. I think there are different ways to do it. But I think I'm not going to use segment tree. That just feels too complicated. So what I will do, right? What I will do is another heap, right? Max price. So we create a max heap, and it just has to connect the timestamp with the value. Well, what we can do is, if we have objects, each timestamp is connected to an object, okay? And the object, I mean, it doesn't even have to be an object. I think we can simply, I just need these two to be connected, right? So it can be simply like, say, a list, right? A list. And that would just be price. So when I change the value, we will be change the value inside the list. And then when we put the list in a heap, we put the address in it. So if we change, the value shall change. You know what? We need to test this. I'm not 100% sure. Okay. So here's my idea. So we're gonna do heap q, right? And then we say this is gonna be, let's say, I don't know, let's say 4, 5, 4. No, it's okay. 3. How about this? Okay. Then we say heap equals list. No. Well, that's fine. Let's say list full.values. And we say heap q dot heapify heap. And then check heap. Okay? So this is right. And then what we do is I always say full to 0. Right? We change this value to giant value, so 100. And heap is this. Heap changes. So all we need to do is heap file again. Then we check heap. Boom, 4 goes into the first. So that is what we're gonna do. I'm using that structure. Yeah, so once we figure that out, it's not that difficult. Okay. So, a couple of things that we need to work. Hold on. This one's correct. 1110. Yeah, we'll keep a min heap, keep a max heap. Ooh, keep a min heap is easy. Max heap. Are you going to... Dang, man. 2 of them? I guess that's the only way, right? Because min heap and max heap are different. Yeah. I'm still thinking. Yeah, we need to keep both. That's kind of a waste. We can't just do one. Hey, I guess we cannot. Unless the heap itself has like a key. But I don't think heap has a key. We discussed this. We have to put a key inside the object. But now we have 2 objects. That's the thing. And when I update, I can't just use the same one. Damn, so I have to use both. So we say self dot, oh, let's get a heap. So we have self dot timestamp ts, okay, ts heap, max heap, min heap, okay, and then ts price positive, ts price negative. Damn. Okay. Update. Well, update. We're gonna say if timestamp is not in self.ts. No. This is also a max heap. This is also a max heap. This is a price. This is also a max heap. So TS price, right? If it's not in it, then say TS price positive timestamp equals this. Price, what's the price? I'm gonna say price is 0. Alright. Then we say TS positive timestamp 0 equals price. And self. And then we're gonna do we're gonna do the negative. Right. So we have a negative. This will be negative price. That's the update, right? Current. Oh, hold on. Timestamp. If it's not, then we say heap q dot heap push self dot timestamp heap, but it's a max heap, so we have to do minus timestamp. Okay, so the current will take the top, so we say ts equals self heap q dot heap. We don't even have the pop. We just say self.ts heap top negative, right? So say self.ts price positive this. Now we return this. This is the current price. Maximum. Have to also this and this and not in, right? So it's a new price. So we'll do this, and then we say self heap q dot heap push self dot ts price positive. So what do we push there? We're just gonna push self dot ts price positive. Oh, we have to do negative as well. Come on. So positive and negative, all right? Positive timestamp. We'll push this in. And then, oh, hold up. Things has changed. Anyway, negative. We'll do this as well. So it's the same, right? It's the same. Just one is positive, one is negative. And then they'll assign a value. It's fine. So before we do this, we say heap q dot heapify maximum self dot max heap, right? And then we're gonna return self dot max heap 0, but this has to be negative. This will be heap q dot heapify self dot min heap. Main heap 0. Okay. That's how I solve this. Is it the most efficient? Probably not. But I think this should be right. TS is not defined. Of course it's not defined because it has to be self dot. Heap push. Huh? Oh, jeez. This is max heap. This is min heap. No, this is max heap. This is min heap. Min heap is positive, max heap is negative. Bad operator type. That is interesting. Hmm? Oh, shoot. That is correct. That's my bad. It's timestamp. Timestamp is just values. All right. I got one wrong. Which one? Current value. Yeah. Don't give me like memory out of range. That would be very unfortunate. Ooh, what? Holy crap. Okay, I did not expect this to happen. Okay, I have some idea. Maybe can help. Let's put it out there. So we don't have the heap push because I heap 5 here, alright? So all I need to do is just this dot append. Then we can turn all of these into O1. Right, this dot append. Dot append. Append. So this is all O1. This is O1. And these are logN. Ooh. Okay. Okay, let's current max. Right. I think I just set them to 0. All right. What we're saying is if self.currentMax is not equal to, which means this one has changed. Okay, if it's not equal to this, then I'll heapify it and self.currentMax equal to this after heapify. And now return self.currentMax, which means if they're the same, I'll just return the same. So this is the same, self.currentMin not equal to minus, no. Self.min, heap 0 and 0. Then we'll do this, and then self.currentMin equals self.min, heap 0 and 0. Otherwise, we just return self.current minimum. Let's see if this one helps. Should definitely speed things up. Okay, have no. What? Oh wait, hold on. This first one is not right. Wait. How's the first one? Update and current. So stock price, update, current. How's it 10? Oh, I did not. Holy crap. Oldest time. Oh, shoot. Current time. Okay. And then everything is append. So this will be the same thing here. If self dot current time is not equal to minus self dot timestamp heap 0. Right, then heap q dot heapify self dot ts heap, and then self dot current time equals minus self dot ts heap 0. Then we will always return self dot current time. Okay, try this. All right, we are correct on the first one, but we're not correct on the second one. Man, it would be hard to see where the error is. Something. How? This is the same logic, right? But if timestamp is not in this, we add the value, right? And then we put a timestamp, the negative timestamp in the timestamp heap, and this put a value in, and I update. So yeah, this looks fine. So current. So I have a current time. So the current time, if it's not equal to the top, which is the biggest time, if it's not, then I'm gonna heapify this, and after I heapify this, I'll get the current time, and then I'll return the price. This should be the largest. Interesting. It's hard to tell which one is wrong. Okay, current max. Because every time I update this value, so this value should change as well. So if the max, oh, I can change something down. Gotcha. No, I don't need this to keep the max. Like, why would you want us to keep the max like this? I can just keep this. It's every time update, I just keep updating. Come on, man. Why are you so stupid? I just need one heap. And current max, current min, That's it. Right? And we'll update the timestamp. Oh, we do need a TS price. We do need this. So if it's not in this, we're gonna say the price timestamp will equal to price. We don't need to do this. We're gonna push this. No need to do this. Actually, I don't even need to do this. I do this, right? And then I say self dot current max maximum current max price. Oh, come on. Yeah, I'm doing it too complicated. This one is very simple. Current mean and then price. Current. So just TS price and this. And I'll just return self dot current max. Return self dot current mean. That shall do. All those complicated convoluted thing, it's not necessary. It's not in here. That means it's a new timestamp. TS price is not defined. Self. Oh, not right. That is interesting. So we have stop price update current maximum update 3. Oh. Oh, wait, hold on. Hold on. No, I cannot do it that way. Shoot. Shoot. Let me think again. Okay. Yeah, we have to use the heap. Is when you change the value, you never know. Right? You change the value, you never know. Can I go back to the previous? Wait, is this one wrong? This one times out. Because if I call this many times, if you just do it many times. This one has error. Oh, that's the error. Oh, we're back to square one. I forgot what did we decide? Current time. And then I add a new timestamp. I see. Every time a new timestamp in, I have to, and I can call. Yeah, every time a new timestamp. You know what? I do think this one shall be heap q dot heap push. I'll put this here, and then this will just be this. It's guaranteed every time a new thing come in, we'll have the max time. But if we want to find a maximum and a minimum, we use this trick. Jeez, that's still not right. What? Man, that's the thing. I don't know, like, if it's wrong for what reason it's wrong. Shoot. I think it's the same, exact same location. I mean, compared to the previous submission, this part is the same. So the only part that's different is this, right? Oh, the self.maximum, yeah. Because I can change some maximum later on. So you have to heapify it. Lord. But either every update you're gonna, oh yeah, then every update you call, oh, this one is just called so it's the number of times so you're saying is I don't know. Let's see if this one will be faster. But we have to call the heapify every single time when we use the minimum or maximum. The previous will be every time we call update, we have to make changes. But we can do like multiple updates and then call the maximum. So the number of calls to maximum could be smaller than the number of update call. But based on the current look, didn't seem to be promising. Okay. So we're gonna change here. Every time a new timestamp come in, right? Yeah, because new timestamp comes in, I can compare to the current largest. If it's not the largest, yeah, the timestamp we don't need a heap queue. Because the timestamp we just need to track the biggest time, and that's it. Okay. The timestamp, because it only increases, doesn't change. So we don't need this. We just need the current time, right? If the timestamp is not in this, then blah and blah. And then we don't need this. We just call self.current time equals maximum self.current time and timestamp. So make sure current time is always the biggest. And then this will just be the current time. Right? And then these will change. Then for these, what we can do, right? So this is the change. So what we can do is to check. And we say, actually we put it here, right? This is the current price. So we change for this timestamp. Now what we can say is if you don't know. Yeah, if I change the timestamp, if this currently is the biggest, I change it to be smaller. You don't know which one is smaller. Okay. So just by removing one piece, let's see if we can make it a little bit faster. Still not. It could also be implementation. How about this? The only time we need to reheapify is if I, after the change, yeah, so I have the top, right? So this is the new price coming in. And I will make the change. And after I make the change, I can check the main heap, right? So I check the top of the main heap. If it's equal to the price, then that means actually what I can do is before I make the change, right? Before I make the change, I can check, right? I can check on the top. Okay, I can check the top. And then after I make the change, if the top, if the top stay the same, that means the change is not happening to the top. Then I can compare my value to the top. If my value is smaller, then yeah, it's fine. If my value is bigger, then I just swap the two, right? And we don't have to do any. So what you are saying is that but how do you know where they are? Right? How do you know where they are? Lord. This is harder than I expected. Keep track of the mean price. Turn to the 9th. I don't think we need a segment tree for this. Just need to be smarter on how we can save the operations. These timestamps, we have those values, right? And then originally, let's say the min heap, so this is the minimum value is here. And the new value we change if it's inside any place and it's smaller than original smallest. But you don't know where it is. But since you're smaller, then I just heapify it. But if I'm bigger, yeah, we can check if it's changed. So what you're saying is, we can say previous to max shall equal to self dot max heap 0, 0. That's the previous max, right? And then I'll do this. And then we say well, first we need to check if the current, if there's any change in the in this max value. So the only time we'll do heapify is, let's see, so we update the price, right? So the updated price, so we say if pre-max not equal to this, which means we change in the front, right? Or price is larger than minus self dot max heap 0, 0. So the current one is bigger, right? So any of these happen, then we will heapify it. And we'll do the same for the minimum. Say previous minimum is the mean heap. Then Oh, shoot. This should be negative. This means we changed the top. Then we're obligated to heapify. This means the price is larger than heapify. Okay, this is the min heap. Min heap is a positive value. If previous min is not equal to or the price is smaller than, any of this happens, then we're gonna heapify. There we go. Oh, no, we don't need these. This and this value is not needed. Oh no. Jeez. It says not enough. You gotta spend more time thinking about this. I still don't think we need to use segment tree. I don't think so. Because it's gonna be logN and no matter what. So if you segment tree, it's gonna be logN as well. And you have the implementation cost. I'm gonna cheat by taking a look at not this one, but this thing. What is this? Update. These are updates. Timestamp and price. Well, for each timestamp, I change the value. I have to wait for tomorrow on this. Yeah. I'll wait for tomorrow to keep working on this. I don't know. This is weird, huh? I do have 2 hints that we can try, but I don't want to use the hints right now. It could be the fundamentally heap is not gonna work. But like, how much faster can you want? This is O logN here. Update is O logN. And these are O01. We'll call it. I'll deal with it tomorrow. I'll see you guys tomorrow. Adios.